Hi, welcome back to my video on population genetics methods. My name is Daniel, and today we'll be continuing on with FST. And today I'd like to kind of talk about more rigorously what FST is, and we're going to build up in rigor. So tomorrow, or next week I should say, we'll maybe talk about like the formulas for it and get into the math. And last time, and I recommend you watch it if you haven't, maybe I'll put some sort of thing here that you can click on to see the video that I made last week. Last week we thought about, how is FST calculated on kind of very high level, this guess the genome game. And today I'd like to talk more about kind of what a given value of FST is. If I give a value of 0.05, what does that mean? What is the meaning of that number? It's sort of a vague thing. I kind of elided what it meant to score better or worse. And I also want to kind of relate to kind of more traditional definitions you may have heard of FST. So anyway, with that out of the way for a little intro, let's get into it. And the first thing I want to talk about is something that I already mentioned before. I'm going to continue to kind of hammer home, which is that FST is not a measure of distance. It's a measure of, I said differentiation yesterday, but I really think it's a measure of differentiability. It's how well can you tell apart to populations. That's the right way of thinking about it. Again, how much better you do playing guess the genome. I want to say though that like FST includes distance. I sort of mentioned it also last time. Like the more different two populations allele frequencies are, the easier it is to tell them apart, the more differentiable they are. But there's other things that can affect that. And I want to kind of give some intuitions for what I mean therein. So I'm going to talk today about starting off with some sort of counterintuitive examples. Anyway, so to start off there, I'm going to draw us a little rat. And this is the wild type rat. I'm actually going to give there two different wild type rats. And this is a cute little rat. Let's give it a little head. It's got some whiskers. Hopefully my rat drawing isn't too bad. And this cute little guy has a genome, or his population has a genome, right? There's a population of rats, and they have some sort of internal variance. And then scientists, being scientists, decide to take some of the rats and make them really inbred, so they're good for experiments, and do some experiments on them. And we now get a population of just really inbred rats. So they have a white fur coat. And that's the main difference. And they're all clones. Every single rat is a clone of the other rats. They're totally inbred, essentially. And then actually, someone also makes another strain of rat, which is pretty close related to this one, but it has a single mutation, and everyone has it in this population. And that new mutation that they have, it basically makes them have, I should also give this little guy whiskers, shouldn't I? It basically gives them red eyes, and this is like the red eye mutation. And so I'm gonna get this guy some red colored eyes. So here are three populations. And I'm gonna just kind of give a list of genes, or SNPs, I should say, a list of SNPs, including the SNP that encodes for the eye color gene. And we'll give this guy regular colored eyes. They'll kind of a wild type, as they say. And yeah, we'll just make a little table here. And here is the population of origin. Maybe make this a bit more clean, but I have lots of space either way. And then there's a bunch of SNPs. And I'm going to give the allele frequency at these different sites. So that's, again, how common the, a certain allele, maybe the T versus the C, maybe the T versus the A. It doesn't really matter, but sort of how common different variants are in these three populations. And I'm going to say that, there's lots of variation in the first population, although everyone has the ancestral eye color gene, or maybe most people do, or most rats, I should say, do, because it's pretty bad to have that. And then all of the clonal lab rats with black eyes have that, the wild type eyes, and none of the lab rats with the red eyes have it, because they all have the variant that is not natural and makes your eyes red. And then we'll say for the rest of the variants, I'm just going to make up some numbers. Try to be random, but humans are bad at being random. Yeah, you know, there's variation there. There's variation there. The second lab rat population, I'm going to say, has also some variation, and then this other, sorry, it doesn't have any variation. Excuse me, it does not have any variation because they're all clones. So everyone will have the same variance, and this other one, which is closely related to it, will likewise have have no variation, and they'll be the exact same genomes as the first lab rat. So lab rat 1, lab rat 2, and this goes on forever, not forever, but like for a million sites. Lab rat 1 and lab rat 2 have the same genome except for a single site, and the entire population of both are clones. And at that one site, they're totally opposite. Versus the wild type rat has lots of diversity because it's a wild type rat. So if you were to compute the pairwise FST using our little guess the genome game, which if you haven't already watched the video, and I do recommend, it's sort of how much better do you get at guessing the rat's genome after you learn which population of rats it comes from. So let's start with the wild type rat and just some other rat. Let's say the first lab rat. Well, there's internal diversity, so we'll do better by learning the population of origin, but it should be clear that we're not going to always win. We're not going to always be perfect at guess the genome. So if we see this site where maybe the average allele frequency here between the two populations is 0.6, and then we learn that it's actually 1 versus 0.2 or something, we've done a lot better then. We've greatly improved our score. So we're going to have some sort of FST. I don't know what the value would be, but let's just say it's equal to x. And so the FST of these two is x. Similarly, if we compute the FST between these two, it's actually going to be essentially the same with a single site varying. So I guess the FST will be a little bit larger for the second lab rat because there's a slight difference in this site where you're definitely going to get better at guessing here than at here. Like the relative increase in information is a lot larger because they're much more distinct, these allele frequencies, than 0.9 and 1, 0.9 and 0. But ultimately, it's not going to be a huge impact on the whole genome because most of the genome is the exact same between these two. And so we'll call it y, but y basically just equals x plus some tiny number epsilon. And so essentially it's the same. And we'll say for basically what we know is that 0 is going to be less than x because essentially the FSTs are, you're clearly getting information. So we're doing better at guess the genome, or sorry, guess the gamete, I guess is what I call it. But we're doing better at guess the gamete. And so, it's going to be a non-zero value, but it's going to be worse than 1. And also y is going to be slightly better than x. Oops. It's going to be worse than 1. We're not going to get all the information, right? Because essentially, the population has some internal diversity even after we correct for the, which group it comes from. Because the FST here, when we play guess the gamete, we might do better when we learn that at this site it's from the wild type versus the lab rat, but we're not going to be perfect because there's still diversity in the wild type population. Hopefully that's all clear. So everyone should get now that if we compute the FST pairwise between the wild type rat and either of the two lab rat strains, it'll be some number between 0 and 1. And it will not be 0 or 1. Let's think about playing guess the genome now guess the gamete for the two lab rat strains. So if we play guess the gamete for these two lab rat strains, well, we don't get any information that we didn't already have for every site like this one, but we already had that information. We already have all the information. So it's not, I kind of went over this last time, but at sites where both populations or all populations are matching and they're fixed in the same direction, we sort of just ignore those sites. And actually they kind of fall out of the math in some way realistically. And if you were to compute them, they would be sort of undefined, because essentially these sites are, when we play guess the gamete, we don't do any better because we didn't have anything to gain. Like we gain nothing because we had it all already. And so FST is just sort of undefined here, and we actually essentially drop these sites. We don't even look at them for the FST. There's only one site which affects the FST of this population. So if you remember, you may already be getting to where I'm getting, that the FST, when you have a fixed opposite, well, how much information do you gain? You gain all of it. You instantly gain the entire information. So in this situation, the FST is actually 1. So the FST between the two lab rat strains is equal to 1. That is crazy. So that is saying, if you are looking at FST, that the populations of these two, if you think of it as distance, the two lab rats could be thought of as being more distant, which is obviously ridiculous. Obviously, they're almost the same, but if you think of FST as distance, it's kind of weird. But it's not weird, actually, because FST isn't distance, it's differentiability, which again, being more distant does make you more differentiable, but in this case, these lab rats are perfectly beautifully differentiable as they are. Because if I look at a single genome of a rat, I instantly know which population it came from. If I look at this rat's genome, someone gives me a lab rat genome, and I know it's going to be one of the two lab rats, I just have to look at the first SNP, and I'll instantly know everything about it. Additionally, when it comes to the lab rat genomes, I can also predict a lab rat's genome perfectly based on knowing its population. If someone had me play guess the gamete with one of these lab rats and had me say it out, I could perfectly recite the entire genome, assuming I had a little crib sheet here. So they are fully differentiable. They're 100% differentiable. The FST really is 1. The differentiability is maximized. On the other hand, while clearly more distant to the wild type rat, it's not fully differentiable. If someone said, you have a wild type rat, give me its genome, I would not win. I would make educated guesses. I'd guess some site here, but I'd be right 90% of the time, and then I'd guess some site here, be right 70% of the time, and then guess something here, and get right 80% of the time, and then 60%, and 70%, and 80%, et cetera, all the way down. But I'm not going to be 100% correct. I just won't be. And similarly, if I was to see some part of the genome, I wouldn't know instantly which rat it came from, because if I saw let's say a 1 here, or say if I saw, let's say this is a 20% T and 80% G, and this is 100% G, or say 100% T, I said. So yeah, 80% G, 20% T, and 100% G. Well, if I saw a G, I would not know which population it came from. Well, it's more likely to have come from this, from a lab rat, I guess, or this lab rat specifically. I don't know for sure where it's coming from. So they're not fully differentiable. And so I'm going to get some value that is between 0 and 1, because they're somewhat differentiable. They're not undifferentiable. 0 would imply that I kind of can't differentiate them at all. But I can differentiate them to some degree. So that basically is the the first example of why FST is not distance, and why it's actually differentiability. Okay, let's do another example. The next thing I will say is about Neanderthals. So a kind of classic, famous PopGen result that was really shocking based on what people thought they knew in 2006, but now everyone post 2012 knows the answer. Humans who have ancestors that left Africa have Neanderthal ancestry, and this includes not only Europeans and East Asians, who actually have more than Europeans, and Papua New Guineans and Native Americans, but actually also people, let's say, in North or East Africa who have ancestors who moved back into Africa from Eurasia. Anyway, so if you are any of those people, or have partial ancestry from any of those people, you have some Neanderthal ancestors. And a question you can ask, and unfortunately we don't have genomes of these people, but you can do simulations based on what we know about the out-of-Africa bottleneck. And you can sort of ask a question where if we have sort of the human population, and then maybe Neanderthals split off first, and then there's people who stay in Africa, and actually this should be much shallower. And then people who leave Africa, and there's like a strong bottleneck here. There's basically a really strong bottleneck in the Eurasians, and then they remix with Neanderthals. It's a little bit actually it goes in, but it's some. And then you get modern day Eurasians, which I'll just kind of draw here. And then we have modern day Africans, and there's no bottleneck there, so we'll just draw it more simply. So if you were to look at these populations and say, okay, I'm going to draw 2 time points, basically. We simply do a sample here, and we'll say it at T1, and then we do another sample here at T2, and we're going to sample both. And then we'll get a big sample from both. We'll get like 50 individuals from both. So we have good data. And then we say, okay, well, what is the FST here versus here? Has it changed? The intuition, if you think of FST as distance, is that it will go up, which makes sense because this branch is very long and it's deeper than these two. I mean, these populations come together much longer ago, and the Neanderthals themselves are sort of inbred, which sort of increases the distance in some way. And so you'd say, well, it's going to increase. It's going to increase. There's been more time. There's been this admixture from this really deep population that's an outgroup to both Eurasians and Africans, and also, the population is pretty drifted. The Neanderthals are pretty drifted. But you'd actually be wrong if you said that. Because, again, it's not distance. It's how differentiable the populations are. And basically, when you take this time point, I'll maybe write it as FST T1 is greater than FST T2. If you were to look at this population, they're pretty differentiable already because the out-of-Africa bottleneck just happened. So the Eurasian side, at least, which is the only one that really has things happening to it in this example. The African population is just stable. So we can kind of focus on what's happening with the Eurasians. And before T2, they've already, or even T1, they've already experienced the out-of-Africa bottleneck. So they're very inbred. And because they're very inbred, they're relatively easy to differentiate from anything else. Because like the lab rat before, they have sort of extreme values for their allele frequencies. And that means that, oftentimes I say, oh, I see a T. That's got to be a Eurasian, a Proto-Eurasian. Or, oh, it's a Eurasian, so it has to be like a G, because I just know because that they have so many Gs or so many Ts, whatever it might be at that site, at a given site. And so, you can learn a lot about how, if a person is Eurasian or African, and or using that information, you can learn a lot about their genome, because the Eurasians are super inbred. If you learn that it's an African person, it might not be as useful, that's sort of, bad news bears. But if you get a Eurasian, you say, wow, this guy's super inbred, and I know exactly where his genome is. All of a sudden, you then introduce some Neanderthal ancestry. And while the Neanderthal ancestry is also pretty easy to predict if we were to compare it to the African ancestry, it's actually a lot easier to predict because they are more distant, and they've also, the Neanderthals themselves are pretty inbred. But it's like now there's 2 different things that you could have in the Eurasian genome. You could have the original Eurasian type of genome, or you could have this kind of very weird Neanderthal genome. And there may be diversity which was lost due to this bottleneck that is still preserved or even is like novelly added by the small amount of Neanderthal ancestry. So it's not much ancestry, just about 2%, but this little noising event essentially makes it way harder to distinguish the 2 populations. The 2 populations being Eurasians and Africans. I also should say, of course, Africa is not a single population. This is a paraphyletic thing, and maybe I'm talking about East Africans here, or South Africans, or West Africans. But this is just a little toy model. Regardless, you can actually simulate this. I encourage simulating and trying things and looking at data. So I recommend using something like MS Prime to do this. Essentially you can run a little simulation and you'll find that the FST goes down afterwards, which is so shocking. That's the crazy thing. Despite getting this admixture from a deep source, that should in theory pull you away, the added noise makes the FST get lower. It becomes harder to differentiate African genomes and Eurasian genomes. So this is all very interesting, and that is our second example. And then while continuing on about the real world, I'll give my third example, which is that if you take the FST between, so let me make sure I'm not missing anything. Okay, good. If you take the FST between, let's say, an Amazonian population, which has gone through not only the out of Africa bottleneck, but then also the into Americas bottleneck, and then there's actually even population-specific Amazonian bottlenecks. So Amazonian, hopefully I'm spelling that right, 1, Amazonian 2, it's about equal to 0.1. And then if I take FST of, let's say, Yoruba, which is a person in West Africa, and then we'll say French, which is a European person, that's also going to be about 0.1. And then I'm going to take FST of Yoruba, Yoruba, and Han, which is a East Asian population. It's basically Han. It's like the Chinese, basically, for people who are not familiar with these terms. And that's about 0.1. And then I'm gonna, last but not least, I'm gonna take the FST between that European person, the French, and then the East Asian person, the Han. And wouldn't you know it, it's about 0.1. And so if you think of FST simply as distance, this seems to imply that the separation time, maybe, if you think about separation time, between Amazonians who only made it into the Americas, maybe at most 25,000 years ago, but probably much more recently than that, and only diverged from each other even more recently than that, is the same as the out of Africa event, which these two are the same, and maybe that's just the out of Africa event, and that actually the split from East and West Eurasia also happened at the same time as the out of Africa event, which we don't think that's the case. It seems that the split from Africans happened between, let's say, West Africans and Eurasians happened before the split between East and West Eurasians, which makes sense. And we think actually there's a long time between those two events, and we think that Amazonians diverged from one another much more recently. So why are all these values the same? Well, it's because I kind of already was hinting at it, but these two populations went through 3 bottlenecks. And these two, or I'll went through 1. And it's a big bottleneck. And so if you kind of think about it, there's almost like, in some way, maybe 6 bottlenecks you can think of happening here, or at some level. And there's 1 bottleneck happening here, and 1 happening here, and 2 happening here at some level. Just like the decrease in diversity, there's like how much decreases in diversity are there total. And so because there's less diversity here, even though those populations are not that different, they share relatively recent ancestors, they're not very diverged from one another in temporally, they actually are easily differentiable, because again, their genomes are very much closer to being the same when you look at a given Amazonian from the first group, and then a second Amazonian from that first group. They're going to be quite closely related due to small population sizes. And that's also true for the Eurasians, especially if you compare them to West Africans, who are extremely diverse, actually. I could be wrong, but I'm pretty sure they're more diverse also than East Africans or South Africans or hunter-gatherers in the rainforest. And so West Africans basically have an exceptional amount of diversity in their genomes, and this makes it harder to distinguish them from anyone. And so even though the Yoruba are, of course, more different from the Han than the French are, when you compare the French and the Han, you get that they're about as differentiable. And that's true. It's harder to differentiate anyone from the Yoruba because there's more diversity there. In the same way, it's easier to differentiate the Amazonians from one another. And this hopefully builds another way in which you can see that this is not a measure of distance, it's a measure of differentiability. Again, I don't want to say that distance is not playing a role here. It definitely is. If you were to compare populations that are very diverse, equally diverse, and you hold that kind of constant, then the temporal divergence state plays a much larger role. But because human populations and animal populations and all populations are not equally diverse, there's sort of multiple things pushing up and down on FST. It's sort of a complicated statistic. We'll talk about that more. It's not that complicated formulaically, but you can see it when we go into the formula that there's things pushing in multiple directions on FST, and it makes it sort of a more complicated statistic than just a measure of distance, and it shouldn't be thought of that. Or you can run into these sort of semi-paradoxes or sort of learn things that aren't actually true. I also want to basically say that FST is I've actually been doing the same thing I'm going to say you don't need to do, which is to talk about it in terms of pairs. I talked about the pairwise FST between the different rat populations. I talked about pairwise FST here between these different human groups. I talked about pairwise FST when we played Guess the Gamete. So I was focusing on this sort of pairwise nature of FST, but it doesn't need to be pairwise. You can think about how much information you got if you were to play sort of a 3-person Guess the Gamete. I want to talk about more standard definitions you might hear about FST, which are kind of the ones you'll hear generally in a textbook, and how it relates to what we're talking about, which is I don't think the way I'm explaining is unstandard. I think people do think that's differentiability, but you'll often hear about it in terms of variance explained, or heterozygosity. And so I want to relate to those things. And I guess I said I would be going to the formulas next week, and that is true more for how to actually compute FST, but I'll give sort of a high-level overview here where we talk about, let's say, what it means for there to be heterozygosity. So heterozygosity is a measure of how many heterozygotes you have. So if you have some allele frequency, that's the allele frequency of P is equal to 0.3, that means Q, which is like the other allele at this SNP, is going to be 0.7, or 70% of them will be Qs and 30% will be Ps. Well, in the proportion of diploids, again, where humans are diploid, we have 2 genomes, or we have 2 copies of our genome, one from our mom, one from our dad. So the number of P squareds is going to be, or homozygous for P, is going to be 0.21. Hopefully that's, wow, that's bad math. That's 0.09, and hopefully that's obvious, just some simple math. The number of PQs, of heterozygotes, is actually 2PQ, because you can either be sort of a Q first and then a P, or a P first and then a Q, and so it's 0.21 times 2, which is equal to 0.42. And then last but not least, the number of Q squared are going to be equal to, or the number of homozygous Q is going to be equal to 0.49, which is Q squared, basically. And so it's how many of these do we have? How many of these heterozygotes? That's the heterozygosity. And you'll notice that the closer we are, and maybe I'll leave this as an exercise to the viewer, and you can pause it and think about it, but the closer in which P and Q get to 0.5, the more heterozygotes there'll be. That's just going to be the truth. If you want to have the maximum heterozygotes, which is about half the population be heterozygotes, you have to have a P equal to 0.5 and Q equal to 0.5 as well. And so that basically means that as the heterozygosity goes up, the noisiness also goes up in the genome. And essentially, you can sort of think, if you think of like HT is sort of the heterozygosity in the total population, and then, let's see, heterozygosity in total pop, and then I'm going to say HS equals maybe like the het, I'm just going to abbreviate it, in subpops. And you can think of that sort of as maybe like HS1 plus HS2 plus HS dot 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 divided by n. So like, you know, we'll maybe put, or we'll move our dot 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 and put HSN plus dot 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 plus HSN. So we're sort of averaging over the heterozygosity. So sort of like, what is the heterozygosity in the total versus sort of the average heterozygosity in subpopulations? Well, FST is then going to be equal to HT minus HS divided by HT. So it's basically how much heterozygosity is explained away by sort of population structure. So if there's no heterozygosity left, if we can fully differentiate the subpopulations, there's no heterozygosity within them, they're all clones, then this will be 1/1, which will be 1, which is kind of what we thought of before. And if the heterozygosity in the subpopulations is the exact same as the heterozygosity in the total populations, we've learned nothing, well then it's x minus 0 over x, or excuse me, it's x minus x over x, which is 0 over x. And so we'll get 0. So these sort of extreme values still make sense. And again, if the heterozygosity in the total is 0, you're going to get 0 minus 0 over 0. So it's kind of weird and confusing. Yeah, hopefully that makes sense. You can also term this in sort of variance, which the variance is sort of how it's like a measure of how widely spread some distribution is. So if there's more variance, it's sort of like, if let's say you roll 2 dice, there's some sort of variance in the number that you get on the die, and you might notice that numbers like 7 are more common. And so if you roll different numbers of dice and do different things, so there's be different amounts of variance. If you roll, for example, a let's say 11-sided die, and add 1 to the number, so you get the numbers 2 through 12, you'll get a more even amount of it's a different distribution than if you roll 2 dice. And basically, the further spread apart the distribution is, the more variance it has. And you may be thinking, then, if you have more heterozygosity, you're going to get more it's more diversity. It's more spread apart. So you can instead think of this as this is a sort of term that means variance. The variance in the total population minus the variance in the subpopulation over the variance in the total population. And so all these definitions basically are the same thing. It's sort of saying, we have some amount of noisiness before, and then we reduce it because we kind of lock it up into the subpopulations. And if we are able to fully reduce it, if we have no variance left, then we sort of have fully absorbed it, and we have an FST of 1. And if we can't get rid of all the noise, there's still information to be gained, then the FST will be less than 1. And if we gain nothing at all, then we've got an FST of 0. Okay, so that's just a little thing. I promised I would talk about what an FST means, like what a certain number means, like a number of like 0.3125. And I will talk about that now, because I think that we have like a nice idea of sort of how how this number comes about, basically. And another way of saying, basically what we're saying is how much better do we get against the gamete, right? If that's sort of all these things, right? If there's less heterozygosity at the end, then we're going to do better at guess the gamete. If there's less variance at the end, we're going to do better against the gamete. So what are other ways in which we might do better against the gamete? Well, what if I told you, rather than the population of origin, I told you about some individual's family member? So instead of saying, oh, this person comes from the blue population rather than the red, I say, well, this individual is they have a mom who is a full sibling to someone else's dad, and I also have their genome, and here is our mystery genome, and here is this other person's genome, and they share this DNA, and they share this DNA, and then they share this DNA. And if I'm probably not getting an eighth, but this should be roughly an eighth because they are first cousins. So they roughly should have, this should be about, roughly we should know about 12.5% of the genome. And there's, of course, some variation within that. Some cousins share a bit more. Maybe it's 14%, maybe it's 10%, but it should be around 12.5% if we have a cousin on average. Well, I'm going to, let's say I not only know that they're cousins point blank, but actually I know that, that these regions, these exact regions are the same. They're exactly the same, and they maybe come from, actually, we'll maybe recolor this region maybe into blue instead. And we actually know that these parts of the genome come from like these ancestors, right? So like there's this shared ancestor here, and we just know the genome. Well, I'm going to play guess the gametes, and I'm not going to do any better than the total population because I don't know the subpopulation at all, or maybe there even isn't one, at the sites that are not in this 12.5%. But at those 12.5% of sites, I'm going to do perfectly. I'm going to instantly win the game. I'm going to gain 100% of the information. So on average, how much information did I gain? Effectively, compared to like baseline, I've gained about an eighth of it. And even though it's going to be 100% at some sites and essentially none at others, the way that FST works, as I kind of mentioned before, is sort of average over the whole genome. And so when we average over the whole genome, I'm going to gain about an eighth of the information. So this is roughly equivalent to an FST of, in like amount of information gained, about knowing someone's cousin versus knowing what population they're from, of about 0.125. And so you can sort of think, for example, if you have two Amazonians, that knowing which subgroup they're from, whether they're from Amazonian group A, let's say Caritiana versus Sarui, if I know that someone is of Caritiana origin rather than of Sarui origin, I've basically learned as much about their genome, kind of, as if I knew who their first cousin was and had that person's genome and kind of knew which parts of the DNA were there. I guess maybe it's the same also if you didn't know and you just sort of guessed entirely the cousin's genome, but I'm actually not so sure about that. I don't know exactly how that plays out. That probably is the same as well. So maybe you don't need to know which parts of the DNA. But regardless, it's roughly the same as kind of knowing the person's cousin. On the other hand, let's say that we instead have a more distant relationship where it's actually those people's children. And so now we have a second cousin. And let's say we'll keep the colors, and they just inherit this blue strip, and this is only about 3.125% of the genome. So it's roughly equal to an FST of, instead of 0.125, of 0.03125. And so I actually don't know FSTs of world populations, I don't have them memorized, but I think it would not be out of the realm of possibility for the FST between, let's say, someone from Italy and someone from England to be around this number. So if I know someone is, if I either have a pooled population of English versus Italian, and I only have those two populations. Again, you could do multi-FST, but you'd get a higher value, so let's just keep it as a pairwise thing. So if I only know those two populations, and then I know I know, oh, it's not, instead of being a random person, it's actually an English person. Well, I've learned about as much as I would learn if I knew that someone was sort of someone else's second cousin. I had their second cousin's genome. I want to also state that or you can simulate this actually. You can try it, and I actually encourage that. MS Prime lets you run with pedigrees, so I should encourage that. I want to state something kind of interesting though, which is if you had a population of cousins. So let's say you had some sort of Genghis Khan figure who had a bunch of half siblings, and all those siblings have a child. They're not full first cousins. They're like half first cousins. They share about 6.5 or 6.25 of their percent of their genome. So if you had someone like that, and then you had all these cousins, the like FST between that pool of cousins and their the rest of the population, so they all come from a homogeneous population, and all the ancestors do too. So it's not really Genghis Khan. It's like Genghis Khan, but only in Mongolia maybe. The number of cousins that you have, actually, as you increase the number of cousins, the FST between the cousin pool and the overall gene pool reduces, actually, because it's you get the kind of the most power. You just have like a single pair of cousins. As you get more cousins, well, the parts of the genome that they share are going to be reduced. So that's one thing. You have kind of less overlap between everyone. And additionally, another way you can think about this is you'll have more ancestors. There's more sort of grandmas introduced of every generation, as well as on the other side, the other grandma, the other grandpa. So all of these kind of half first cousins, as you increase the number of them, the FST is not going to trend towards 0.625. It's going to trend towards something lower, basically. Okay, so I think that is more or less enough for today. Next time we'll get into the actual formulas, but I think maybe the thing I want people to understand most is this video, actually, which is what is FST? Why is it not just distance or difference? Why is it differentiability? And then also kind of what is a number like 0.012 mean? If I have an FST of 0.01, what does that actually mean? And how is it different than an FST of 0.03? How much different are those things? Well, hopefully you know now. Hopefully you have a feeling about it's, you can either relate it to families, or you can just think of, well, I gain 1% information versus gaining about 3% information. Hopefully this has made FST a lot more intuitive. And you have questions, leave them in the comments. If you like the style, let me know. I have another maybe thing I'll experiment, but people seem to at least not hate the Blackboard style or whiteboard style, so I'm keeping it for now. I don't know, I might edit in something else, but I think this is the end of the video. So anyway, thank you so much, and see you next week.